Hey, calculus class. So today I would like to talk about the L'Hopital's rule. So this one would be for sections 4.4. It's also about the limit. So this one is the new strategy about using L'Hopital's rule to find out any complicated functions limit. Okay, so we'll take a look at that, the notes, in just a sec. So here's the one, indeterminate form and the L'Hopital's rule. Indeterminate form, so the limit may or may not exist. So anytime that you see anything that's considered infinity over infinity, so after you plug in a number for the value of x for the limit, so sometimes you'll see the form is given as infinity over infinity, 0 over 0, infinity minus infinity, or 0 to the 0 power. A lot of people might be claiming this one is like 1, but we don't know what that is. Infinity to the power of 0, 1 to the power of infinity. They all consider indeterminate form. Indeterminate form, we don't know which one is bigger or smaller, and we cannot determine um, what kind of exact value the structure is. Okay, so we'll take a look at that. So L'Hopital's rule. If limit f of x over g of x as x approaches a shows any of the indeterminate form, then the limit of f of x over g of x as x approaches a is the same as the limit as x approaches a of f prime of x over g prime of x. So basically what this one is saying that anytime they see the indeterminate form with the structure like this, and you can always take the derivative separately, top and the bottom, for f of x and g of x. So once you end up with like a simplification for that derivative, you can use that to find the limit. Okay, so we'll do some practice problem in just a minute. So here's the one. So find the limit using L'Hopital's rule if it's necessary. Okay, so we'll look at that, the first one. So we got A, B, C, D, E, and F. Also, we do have more example coming up. Okay, so now let's do the first one together. And I'd like to turn to the new slide for this. So let me put in the new slide so I need more space. Okay, so the first one we do have, okay, part A. So limit as x approaches 1, and the function is x squared minus 1 over x squared minus x. Well, let's just plug in a number and see what happens. If we just plug in 1 for x, we got 1 square. 1 square, it's 1. 1 minus 1, so it's 0. And down the bottom, so 1 squared minus x. So 1 squared minus 1, it's also 0. Again, 0 over 0, that's the indeterminate form. So basically, we can just take the derivative top and the bottom separately. Now again, we're taking the derivative separately, not using the quotient rule. Okay, so just take the derivative individually. So we do have 2x over derivative of x squared minus x, 2x minus 1. Again, plugging that 1 again and see what happens. So 2 times 1, so we do have 2. So 2 times 1 minus 1, so we do have 1. So eventually, that means the limit is going to be 2. Now, what about another approach for doing this? Back to chapter 2. The way that we do it, it's by factoring it. But sometimes it doesn't guarantee that the function is factorable. Well, this one does. Okay, so factor it. So difference of 2 squared, x minus 1, x plus 1. And then the denominator, so take out the greatest common factor, so take out x, so we do have x times the quantity of x minus 1. Cross out the restriction, so we left with x plus 1 over x. And then this one basically plug in a number, 1, so we got 1 plus 1, so 2 over 1. So you can use either one of those techniques to find the limit. But I do recommend you to use the L'Hopital's rule because it's the indeterminate form. Okay, so now what about for part B? So part B, so we do have the trig functions. A lot of people kind of afraid with the trig functions. So limit, x approaches power 2 from the right-hand side. It's a one-sided limit. So it's cosine of x over the quantity of 1 minus sine of x. So cosine of power 2, we do know that's 0. Sine of power 2, that's 1. But 1 minus 1, that's nothing. So 0 over 0. Indeterminate form again. So that means we take the derivative top and the bottom separately. So derivative of cosine of x is negative sine x. And derivative of 1, that's 0. And then derivative of negative sine x, then that would be negative cosine x. So this one is just the derivative of tangent. Well, I mean the function is just considered tangent. So we try to simplify it. So tangent of x. So tangent of pi over 2 and tangent of pi over 2, according to what we got, it's 1 over 0, which is undefined. Now, got to be careful with this. This one is tangent of pi over 2 from the right-hand side. So back to the parent graph of tangent. So tangent is just like the cubic curve and is being bounded by the vertical asymptote, negative pi over 2, pi over 2. So it's going this way. So what do you notice? If the limit as x approaches pi over 2 from the right-hand side, so that means coming from this side right here, so that means the limit is going to be considered positive infinity. Again, this one is not actually 1 over 0, it's 1 over 0.0000 blah 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 1. So it's a 1 over a very small number, so that's why it's infinity. Okay, so now let's see the rest of the example here. So for C, okay, so I need a new slide for this. Okay, so now let's see what that is for C. So we do have limit, and then t goes to 0. So e to the power of t minus 1 over t to the power of 3. So plugging a number, e to the power of 0, so that's 1. 1 minus 1, 0. 0 to the power of 3, so that's nothing. Again, indeterminate form, so that means we can take the derivative, top and bottom, separately. So derivative of e to the power of t, so that's e to the power of t. And then derivative of t to the power of 3, so it's 3t squared. And then plugging a number, so e to the power of t, so e to the power of 0, that's 1. And then 3 times 0 squared, so 3 times 0 squared, so that would be 0. Again, this one is just giving you that 1 over 0.0001, which is considered infinity. And also by comparing and contrasting, so this one right here, this one shows the exponential growth. And this one is just the cubic growth. So obviously the rate of change for the top function, it's higher compared to the rate of change of the bottom function. So eventually, so it's going to be infinity. Okay, so now let's see what else that we have. So for D, we do have limit as x approaches 0 of the function of tangent of px over the function of tangent of qx. So again, you try to plug in a number, 0, so tangent of 0, so it's always nothing. So tangent of 0, that's 0. Tangent of another 0, so 0, so 0 over 0, indeterminate form. And now using the L'Hopital's rule, so limit, so x approaches 0, so derivative of tangent of p of x, so which is secant square px, but don't forget about the chain rule, so times p. And then derivative of tangent of qx, similar, so secant square of qx, but don't forget about the inner function, qx. Derivative of qx, that's q. So secant of 0, which is considered 1, so 1 squared, that's 1. Same thing down the bottom here, same thing happened down the bottom, so we do left with p over q. And then that's going to be the limit. And now let's see what else that we have. So for part E, so far all the example that we have is they're relatively easy. So just plug in a number. If that's considered indeterminate form, so we just use that, take the derivative, top and the bottom, and then find the limit. So now for part E, the continuation, so we do have limit. X approaches 0 from the right hand side, so the function of natural log of x over x. So again, natural log of x, so the function looks like this, the parent graph. So 0 approaching from the right hand side, so that means coming this way, so that one would be considered negative infinity. And then over here, so this one would be considered 0.0001. Okay, so you may notice, so this one is just considered negative infinity over a very small number. Or you can do it separately, so you can just say that it's 1 over, okay, let's see. Just want to use the eraser here. So it's 1 over 0.00001 times negative infinity. So 1 over 0.00001, so that's infinity. So we do have infinity times negative infinity. Now keep that in mind, infinity times negative infinity, that's not the indeterminate form. So eventually this one is going to be considered negative infinity. Because positive infinity times negative infinity, positive times negative, so it's negative. So infinity times infinity, that's just another bigger infinity. So eventually the final limit is going to be negative infinity for E. And now let's see what else that we have for the rest of this. And what about for F? Okay, so now here's another slide. Part F. So we do have limit. And then x approaches 0. So e to the power of x minus 1 minus x all over x squared. Again, plug in 0, so we got 1 minus 1, so that's 0. 0 minus 0, that's nothing. 0 squared, 0. So basically we can just take the derivative, top and the bottom. So derivative of e to the power of x, e to the power of x. Negative 1, constant, derivative of a constant, nothing. Derivative of negative x, negative 1. And then it's over 2x. So now let's plug in 0 again and see what happens. So e to the power of 0, that's 1. 1 minus 1, nothing again. 2 times 0, 0. Another indeterminate form. So what we can do, we can just take the derivative one more time. So e to the power of x over 2. So now this time, so the limit is going to be appearing here. So e to the power of 0, so which is 1 over 2, which is 1/2. So sometimes once you deal with the indeterminate form, so that appears twice, so that means you want to keep taking the derivative over and over again, top and the bottom, so you get to the limit. Okay, so now let's see what else that we have. So we got G, H, I, and J. Okay, so let's do G right here. So for G, we do have limit, x approaches 0, and the function is 1 minus cosine of x over x squared. So it's the same kind of idea that we've been doing. So plug in a number, so 0, cosine of 0, that's 1, 1 minus 1, so which is 0 over 0 squared, 0. Indeterminate form, so take the derivative, top and the bottom. So derivative of negative cosine of x, which is negative sine x, but don't forget about the negative, so it's positive. So derivative of x squared, so 2x. So plug in 0, we do have 0 over 0 again, indeterminate form, so one more time, derivative. So derivative of sine of x, so we do have cosine of x. Derivative of 2x, which is 2. So cosine of 0, which is 1 over 2. So then that'd be the limit. Okay, so this one's for G. What about for H? And for H, we do have limit. So x goes to 0. So we do have cosine of x minus 1 plus 1/2 x squared. And then it's over x to the power of 4. Okay, so plug in that 0, so we'll see that cosine of 0, that's 1. 1 minus 1, that's 0. So 0 squared, that's nothing, so 0 again. So 0 over 0. And then, again, derivative top and the bottom. So derivative of cosine of x, we do have negative sine x. Derivative of negative 1, that's nothing. Derivative of 1/2 x, so then that'll be x. Bring down the power times 1/2, you get 1. Subtract the power by 1, you got 1. So x to the first power. And then it's all over derivative of x to the power of 4, so we do have 4x to the power of 3. So plug in 0 again and see what happens. So we got 0 on the top, and we got 0 down the bottom. So we need to take the derivative one more time. So limit, x goes to 0, derivative of negative sine x, so we do have negative cosine x. Derivative of x, so that's 1. And then derivative of 4x to the power of 3, so we do have 12x squared. And looks like it's going to be 0 over 0 again. So negative cosine of 0, so negative 1 plus 1, so that's nothing. So 0 down the bottom. So we need to take the derivative one more time. So just keep taking it over and over again. So derivative of negative cosine of x. So we do have negative sine x. So negative, negative, positive. So positive sine x. Derivative of 1, that's a constant, so it's 0. Derivative of 12x squared, so 24x squared. Well, 24x. So it looks like it's going to be 0 over 0 again. So one more time. Man, this one is tedious. So derivative of sine x, so we do have cosine of x. Finally, this time it's going to work. Derivative of 24x, 24. So plug in 0, so we do have 1 over 24. And that would be the final limit. And then for I and j, okay, so they're quite similar. So I'll just do I right here. So for I, we do have the limit. X goes to 0, so cotangent of 2x, and then sine of 6x. So now, before you plug in the number, you probably want to set it up as a quotient first. So this one's sine of 6x, so just leave that on the top. Cotangent, we do know that's the reciprocals of tangent. So let's put in tangent down the bottom, tangent of 2x. So again, limit, x goes to 0. So plug in 0, we do have sine of 0, so that's nothing. Tangent of 0, that's also nothing, so it's indeterminate form. So if that's indeterminate form, we can take the derivative top and the bottom separately. So derivative of limit, sine of 6x, so we do have cosine of 6x times 6, the chain rule. Derivative of tangent of 2x, so secant square of 2x. And then times 2, again, the chain rule. So cosine of 0, so 6 times 0, that's 1. That's 0, so cosine of 0, that's 1. So we left with 6 on the top. And then down the bottom, secant of 0, so that's 1. 1 squared, that's 1. So we left with 2 right here, the coefficient. So that means eventually, so it's going to be 3. And then for j, it's quite similar. So anytime they see everything listed on the top, so that means you need to bring something down to the bottom. So the best way you can do it, you can always convert that to the reciprocal form. Well, this one shows the negative exponent. So basically this one can be written as limit x approaches infinity, x to the power of 3 over e to the power of x squared. So instead of using the negative exponent, we can just bring this one back down to the denominator. So we got infinity over infinity. Indeterminate form. So take the derivative top and the bottom. So we do have limit x approaches infinity. So derivative of x to the power of 3. So 3x squared. Derivative of e to the power of x squared, just the same thing. E to the power of x squared. But don't forget about the chain rule. The power. So times 2x. And then before we plug in a number, it looks like we can reduce this one top and the bottom. So we try to reduce. So we do have limit x approaches infinity. So we got 3 half x squared over x, so that's just x. And then denominators, don't forget about that e to the power of x squared. So just plug infinity, we do have infinity over infinity again. So take that derivative one more time. So derivative of 3, so we do have 3. And then derivative down the bottom, so we do have e to the power of x squared again, but don't forget multiply by 2x. So 2 times 2x, then that will give you 4x. So we do have 3 over infinity, so eventually the limit is going to be 0. Alright? Okay, so let's see what else that we have for the rest of the example here. So we got A through F done. We got G to J all finished. Now what about for K, L, M, and N? Okay, so those are the more complicated example. Okay, so we'll look at those in a minute, but let me just write them down so I can transfer that to the next slide. So limit x goes to infinity, so we do have x minus natural log of x for that one. So that's K. L, we do have limit x goes to 0 of the quantity 1 minus 2x to the power of 1 over x. And then for M, we do have limit. That one is a one-sided limit. X goes to 0 from the right-hand side, so 4x plus 1, the quantity, to the power of cotangent of x. And then for N, we do have limit. X goes to infinity, so of 2x minus 3 all over 2x minus 5, quantity to the power of 2x plus 5. Okay, so we'll do some practice for this one. Okay, once again, need the new slide. So now for k. So the way it's given here, so it's kind of weird for k. So it's limit x approaches infinity, and we do have x minus natural log of x. If just plug in infinity, we do have infinity minus infinity, which is another indeterminate form because we don't know which infinity is bigger, which one is greater. So it's hard to determine the exact value of infinity minus infinity. So now here's what we can do for the limit. We can always use the properties of natural log. So this one would be considered natural log of base e to the power of x. And then minus natural log of x. So that one, just rewrite it. Okay. So, because one thing that we notice, natural log of e, that just considered 1. So 1 times x, because the power can bring it down. So that's x. And now, back to the properties of natural log, we can always condense this. Remember that natural log of x minus natural log of y. This one can be condensed into natural log of x over y. So that means this one can be written as limit x approaches infinity, natural log of e to the power of x over x. Okay, so what I did here, I just used the property of limit. It's a difference to quotient. Depends on which way that you want to say it from left to right, because that's condensing, so it's difference to quotient. Or if you try to expand it, it's quotient to difference. And then plugging that infinity, so we do have infinity over infinity. Because e to the power of infinity, that's infinity. X, that's infinity, so infinity over infinity. So this one just gives you the indeterminate form. So basically we can just take the derivative of this, top and the bottom, separately. So taking the derivative, we do have e to the power of x over 1. Okay. And then we find the limit. So the natural log, what about the natural log? The natural log, that's just the operation. We can deal with that later. So derivative of e to the power of x, e to the power of infinity, that's infinity. So we do have infinity on top, infinity over 1, that's just infinity. So then the limit, x, well, as x approaches infinity, so natural log of infinity, which is infinity. Okay? It's a little bit weird structure with this type of problem. So basically what you need to do, you need to condense the expression first. Okay, the binomial. So once you condense it, once you come up with the quotient, you can always simplify it by using the L'Hopital's rule. Okay, so now let's see what else that we have for the next one. So we got k done. So the next one is L. So limit as x approaches 0. So we do have 1 minus 2x quantity to the power of 1 over x. Okay, so anytime they see like a variable with the power like this, so that means you want to separate the function, so you can just set that, let y equals 1 minus 2x to the power of 1 over x. So the purpose of doing this, we can use the properties of natural log. So you take the natural log both sides here, guess what you can do? You can always bring down the power 1 over x. And then from here, we do have natural log of y equals natural log of 1 minus 2x over x. So basically what I'm doing here, I try to simplify the structure. I try to make the right-hand side as the quotient structure here. So we do know that limit x goes to 0. So x goes to 0, we do have 1 minus 0, which is 1. and then natural log of 1, which is 0, just the right hand side for this. And then x goes to 0, so the denominator is also 0. Again, 2 times 0, that's nothing, so 1 minus 0, that's 1. And then natural log of 1, that's 0. So indeterminate form, so basically what we can do on the right hand side, we can take the derivative top and the bottom. So derivative of the top, then that'll be considered 1 over 1 minus 2x. But don't forget about the chain rule. So derivative of the inner function, then that'll be negative 2. So multiply by negative 2. Okay, so that's just the open parentheses. Denominator, that's just 1. Okay, so basically this one can be written as negative 2 over 1 minus 2x. And now let's plug in 0 and see what happened. So plug in 0, we do have 0 here. 1 minus 0, that's 1. And then negative 2 over 1. So then that'd be negative 2. Again, x goes to 0, so I plug in 0 here. Again, the one that we found out, this one is just natural log of y equals negative 2. So in other words, the limit as x approaches 0 for y, so we take base e both sides. So that means the limit for the function, so that is going to be the same as e to the power of negative 2. In other words, it's 1 over e squared. Okay? Again, any time they see the structure with the variable as a power, you can always do it this way. So separate the functions, so set y equals the whole thing, and then using the properties of natural log, and then we can separate them. So that would be a quotient, so we can use the L'Hopital's rule. But don't forget to undo the natural log. The way to undo it, we just simply take the base e both sides, so we can find the limit. So now let's do another similar problem like this. So that's going to be for m and n. Okay, so now for m. So we do have the limit. Okay, give me one sec. This one. So we do have x approaches 0 from the right hand side. So we do have 4x plus 1 to the power of cotangent of x. So we do know that cotangent of 0, that's considered... Okay, so cotangent of 0, that would be considered undefined. Back to the parent graph of cotangent. Okay, so this one, that's 0. So cotangent graph is just like a reflected cubic curve. So reflected cubic curve, it goes this way. So 0, and then pi. Over here is pi over 2. So this one is coming from the right hand side. So that means this one you can say that this part right here is getting close to infinity. So we do have 4 times 0. So that's 0 plus 1. So it's 1 to the power of infinity. Again, cotangent of 0 coming from the right hand side. So this one's positive infinity. So 1 to the power of infinity. So that would be the indeterminate form. So now, again, it's the same strategy like the one that we did previously. So let y equals the quantity of 4x plus 1 to the power of cotangent of x. And then in order to bring down the power, we take the natural log both sides. So cotangent of x times natural log of 4x plus 1. So basically I'm using the properties of natural log. It's called a power to coefficient. And then the right hand side, you want to put it as the quotient structure. So it's natural log of 4x plus 1 over, well, reciprocals of cotangent, then that'll be tangent. Okay, so this one is 1 right here. Okay, so now let's just plug in that 0. So 4 times 0, that's nothing. So natural log of 1, that's 0. And then tangent of 0, so then that'll be 0. So that's the indeterminate form. So that means we can take the derivative top and the bottom for the natural log and then the tangent. So we do have 4 over 4x plus 1, derivative of this. And then derivative of tangent of x, then that'll be considered secant square of x. And now let's plug in the value of x and see what happened. So 0, so 4 over 1, then that's 4. Secant of 0, so then that's 1. 1 squared, that's 1, so it's 4. So that means natural log of y equals 4. And then don't forget to take the base e both sides for the limit. So that means the limit as x approaches 0 from the right hand side, the whole function. So the limit would be considered e to the power 4. Okay. So now let's see what about for n, the last problem. So it's quite similar for n. So this one, limit x approaches infinity, and then we do have 2x minus 3. Okay, so 2x minus 3 over 2x minus 5. So that's the whole quantity to the power of 2x plus 5. So this one is a little bit complicated. Okay, so we do have a rational function, and then we do have a linear function as a power. So again, so you plug infinity, we do have infinity over infinity for the quantity, but also outside we do have infinity. So it's a weird structure here, like that. So obviously the inner quantity, that's already satisfied the indeterminate form. So what we can do, we can set y equals 2x minus 3 over 2x minus 5 to the power of 2x plus 5. So take the natural log both sides, bring down the power. So natural log of this whole quantity. Okay, like that. So if you try to take the derivative of this top and the bottom, okay, so one thing that we notice by using the calculus technique, the limit for this one eventually is going to be 2. So what we have left here, it's natural log of 2. Okay, but outside here we do have 2x plus 5, so it's infinity times natural log of 2. Well, natural log of 1, because 2 over 2, that's 1. So natural log of 1, that's 0. So basically this whole thing right here, if you just find a limit for this quantity. So the limit as x approaches infinity for 2x minus 3 over 2x minus 5. So this one is considered 2 over 2, which is 1. So natural log of 1, that's 0. So 0 times 2x plus 5, which is 0. We can say that's infinity times 0. So let me just be a little bit more specific here. Again, infinity times 0, that's not the indeterminate form. So that's just like a basic structure of the limit. So infinity times 0, that's 0. And then it's natural log of y. And then undo the natural log. So we take base e both sides. So that means y equals 1. And then that's going to be the final limit. So there's another video I'm going to be linking to this one. It's also about the L'Hopital's rule. That's the video I put up there like long time ago. So you guys probably want to watch that one as well. So any question that you have, so make sure that you put into the YouTube channel or the Google Classroom or the School Loop. And I'll see you guys next time. So thank you for watching the video today.